Do you enjoy teaching summer semester?
I should be having fun right now because the semester was so crazy. I'm a graduate student here doing mathematics. So my semesters are always very crazy. So this semester this is a way of making money from the department.
Absolutely.
Yeah, because during the holiday we don't get funding. So you need to look for extra cash.
Yeah.
It's only for 8 weeks. Yeah. So at least the remaining weeks can still have some fun. But it's not fun. Even you guys, I don't know how you guys take classes during
Don't have much of a social life, so.
should be having fun. Me, I don't have a family, so
No.
I don't care. Okay, let's so we'll go back to section 1.8. So and then we finish section 1. Actually, we're remaining with only a small section in 1.9. So let's let's do section 1.8, and this one is introduction to linear transformation. Introduction to linear transformation. So we'll start from the first one, which is the linear transformation. My throat is okay.
How's your week going, man?
Pretty good. I just work and school. That's it.
Yeah,
What about you? Just school?
just school, you know, just trying to finish up my engineering degree,
Which engineering are you in?
mechanical.
Okay.
I was raised by a mechanical engineer, so there's really no hope for me. But yeah, I've been in college far too long now. I think I'm just trying to wrap things up and get my career started.
I feel the same way. I'm like, man, if I don't start doing summer semesters and getting as many credits as I can, I'm gonna be in school forever.
Yeah, it's what it feels like.
So
It's like
long.
5 or 6 years now, and I've been in class. It's not like I haven't been moving forward. And there's 2 years, like I talked about yesterday, but you know, that really set me back. That really pissed me off so much. So yeah, fuck that college, man. This is so much better here. But yeah, I just, you know, getting fatigued now. Like I've been doing this for so many years that it's like a full class load. It's like, God damn, like, yeah, I'm over this. I'm over this. Like, but yeah, I mean, it's moving forward, man. That's all I think. Just keep moving forward.
Yeah, that's how it goes. Eventually we'll finish, I guess.
Yeah, I'll be done when they say I'm done.
Okay, 1.1 definition. So let's define the linear transformation.
You missed the pop quiz.
Did I? How was it?
Except for me. Everybody that didn't show up today. Where is everybody? It's Wednesday, I don't know.
I don't know whether I figured this one was your handwriting.
Oh, yeah, it is.
Okay.
Do you need my name on it or
No, I just.
street?
So most of you guys did not do the worksheet, so maybe I'll still give you a next.
It would have been easier if number 24 and 25 from the first 2 homeworks were on there first.
On the worksheet?
Yeah, no, on the homework. Cause Thursday night when I went home to finish the homework, those were on there.
Yeah.
Those would help prepare for the worksheet. I'm like, oh.
Yeah, the worksheet, I just pulled it out from
Right.
from the homework. Yeah,
But those, they weren't on there at first though, on the homework.
they were not there on the,
So,
All the problems posted right now, is that gonna be all the problems for this week?
no. The issue is, I'm trying to, when I finish the class, then I check the kind of homeworks that I'll give you in each of the sections.
Okay,
Yeah, so make sure you're checking frequently.
yeah, so at least
Yeah, because I usually update after the class, then I go and update the homework.
okay, gotcha.
So, but I will let you know on Friday, on Thursday, actually on Thursdays when I will have posted all the homeworks.
All right, good,
So I will then from next week, then I will on Monday I'll post all the homeworks for the whole week.
all right.
Yeah.
Okay.
But next week we only have like 2 days of class.
Right.
Yeah. I don't
yeah, no Monday, huh?
Yeah, that is when I realized today we don't have a class on Monday. Because I've had a lot of plans. Yeah, so we will only have a class on Thursday, yeah, and Tuesday actually. And Wednesday is the first test.
Gotcha.
Wednesday is?
The first exam. Cool. Yeah. So
I guess I'll come.
make sure you guys agree. Because you don't come with any book and no calculator.
No notes.
No notes.
Okay.
So, but the final exam will allow you to use a small,
Like one sheet.
yeah, a small
Cool.
sheet.
Cool.
I need to double check my arithmetic, like the basic stuff. I need to know that I'm not screwing that up.
Yeah, I'll give you the practice
Yeah.
test with the solutions. And
I'm pretty good at adding and subtracting. I wish there was a major in that. I could get that degree.
Yeah.
Right?
It's so easy.
Elementary education.
So I had to come back to section 1.8 because I realized what you were doing in section 1.9 was a little bit more of section 1.8. So let's go back to section 1.8. So introduction to linear transformation, and we're going to define what this linear transformation is. Definition. So a transformation, which you can write as a T. And this transformation is always like a map, a mapping, a function. So mostly we call it mapping. So you map from one point to the other one. Transformation T, actually from Rn to Rm is called a linear transformation. If T of u plus v, and this u and v are vectors, equals to T of u plus T of v. And C of cu equals to C T of u for any u and v which are in Rn and C, which is an element of real number. C is just a constant, so C is a constant. So it is actually like this, the way I just explained in section 1.9. So this is Rn, and this one is Rm. And this is our transformation here, our T. So we have this U and V here. So this U and V is mapped to this point, and what we get is T of U and T of V there. T of U and T of V. So they get mapped to that other point. So we call this the codomain. Sorry, we call this one the domain and then you call this the codomain. So at this point, this is actually the image. The image. So that is the image. The image. So number one, Rn is called. It's called the domain. Number two, Rm is called the codomain of T. Also this one of T. And number three, for any X which is in Rn, then T of X is called the image of X under T. And number four, the image of T, im of T, which you can say image of T, is the same as T of X, such that X is an element of Rn. X is an element of Rn. Is called the range of T. The range of T. So if you can use this diagram to display all this.
I have a question.
Mhm.
It's totally random, and maybe you explained it before, but what's the arrow over the X and the U and the E? Like, what is the arrow? Is that just the notation that we use?
Oh, the arrow. This is the direction. This is a vector. So it shows that it is not a scalar. So it is a vector, it's just direction. Yeah, it is from the point, let's say 0 to another point. So it's moving in a certain direction. So, but this C here is just a scalar. So this is just a constant. So it's a any number, can be 0, 1, but those are the vectors. So if you're able to use the capital, I mean, if you're able to, you might not, you can say, but I usually like when I just say, I use this. But most of the people, they don't.
So like on the test tool, I have to put something like that. And if you don't put the arrow, is it wrong?
Because you've already said, whether you say it's a vector somewhere. So if you just say it's a vector, then it is fine. But if you don't want to say it's a vector, then you just say most of the textbook, they will just use they call it what? They insist like put more they bold or something. Yeah. Yeah. So most of the books they will use that. But since I've done most of the vectors, I usually put that arrow. So it doesn't matter. So you can use it. So long as you state that that is a vector. Okay. All right. So example number one. Example one. If we let A to be an M by N matrix, show that T from Rn to Rm defined by T of X equals to A of X for X which are in Rn, is a linear transformation. It's a linear transformation. So if we remember, this is actually n. If it is an m by n matrix, then this is m is the what? Is the row, and this one is the what? Column. And that is the column. So the transformation is from the elements in the column, the number of columns, right? The number of, so the vectors, which is in that column, transforming to R to Rn, and that Rn will be the number of rows. Like when we're multiplying the matrix, have we done matrix multiplication? No. Did I show you something like this? No, we haven't done matrix multiplication. I don't think so. Because I will show you how. Do we know when the number of rows should be equal to the number of before you multiply a matrix?
Matrix vector multiplication.
Yeah, so we did it right.
Yeah.
But we did not do the matrix multiplication. No,
Yeah.
not yet.
Just matrix to that.
Okay. So the number of rows, the number of columns should be equal to the number of rows when you multiply the matrix and the vector. So what you get when you multiply, if this is a matrix, let's say if this is an m by n matrix, m by n. So this is the number of rows. So what, and this, let's say this is a vector, and this one should be what? N, right? That should be n. So what you get here when you multiply the two of them here, then what do you get? So you multiply this n by n there. So what do you get? So it's because you're getting, let's say this row, this one, and multiply by this, right? Like if this is U1 and this is U2, and let's say U3 and U4 there, and this is X1, X2, X3, and let's say X4 there, right? So what you should get is like U1 multiplied by X1 plus U2 multiplied by X2 plus U3 multiplied by X3 plus U4 multiplied by X4, right?
Yeah.
So what you should get is, which is n, right? Because you're just adding all these, and you should get only one vector there, one vector, right? So it's only one vector. So in this case here, then when you transform from R to Rm there, then here if you want to, so it is like this. So we have our Rn here, and then we have our Rm here, right? And then we have our transformation there. So if this is our vector x, then the transformation here is T of x. And this transformation is actually similar, which is equals to xx, is equals to xx. Since this x is just a vector, so it is a vector, so it can be x1, x2, x3, like that. So these are elements here. So this is equals to this transformation. So you transform this into now tx1, tx2, like that, until maybe txn. And this is similar to ax. And this ax, and we said this ax, A, since this thing is a matrix, then this A is the same as A1, A2, all the way to what? AN. Then when you multiply by X, then and these X are like X1, X2, X3 to Xn is the same as what? X1, A1 plus like that, Xn, AN, right? Up to that point. So it's the same. So let's prove this. So let's prove. So let's prove. If we let U and V to be elements of Rn, and C to be the elements of R. So what we want to know is, we want to show that this is a linear transformation. This T of X equals to A of X is a linear transformation. And we defined a linear transformation as a transformation from Rn to Rm is called a linear transformation if T of U plus V equals to that, and this one equals to that, okay? So we want to show whether this actually satisfies the two equations there, okay? So we let U and V to be the elements of Rn and C to be the constant. Then the first one we said T of U plus V is similar to, since we said T of X equals to A of AX there, then T U plus V is the same as also AU plus what? Plus V. So it is the same. Then this is the same as distributing, we did this one, distributing the matrix inside here is the same as AU plus what? AV. And this is the same as TU plus what? TV. So the first one is satisfied. So the first one is satisfied. Now, if we introduce the constant T of CU, it is the same as A of what? CU again, which is the same as C of AU. And this is similar to what? C of TU. C of T. So the two of them there are being satisfied. So therefore, so the transformation from Rn to Rm is a linear transformation. So it is a linear transformation. Example number 2. If A is a 4 by 5 matrix, then what must the integer, what must the integer A and B be in order to define a linear transformation? T from RA all the way to RB by T of X equals to A of X for X element of R X element R. So what if we have a matrix A is a 4 by 5 matrix? So what is A and what is
A would be 4, and B would be 5.
what is A and what will be B? A would be what?
Maybe 4.
Look at the
A would be 4 and B would be 5.
look at your previous notes, the previous section.
So in the so 5 and 4. A is 5 and B is 4.
So it is A is from
A is 5.
5, and I said this one is the row.
Yep.
And this one is the what?
Column.
I said this one is the column, and this one is the row. This is the column, and this is the row. So it is from Rn to Rm. From Rn to Rm. So, solution. Since Ax is defined for each X element of Ra, A is equal to the number of columns of A, and so A equals to 5. And since Ax is also an element of Rn, since Ax is an element of Rb, of Rb. So the first one we said A is an element of Ra here. So we are actually transforming from A, T of A. So it is here to that point. So this is Ra and this is Rb. And this A, X is an element of Ra, and A of X is an element of what? Rb. So what we get there is Rb. So since A of X is an element of Rb, then B is equal to the number of rows. And so B equals to 4. B equals to 4. So you should be so careful with this. So it is from the number of columns to the number of rows. To the number of rows. Example number 3. Define the linear transformation
Excuse me, thank you.
T from R2 to R3 by T of X equals to A of Ax for X element of R2, where A equals to 1, 2, 3, 2, -1, 0. Number A, find the image of U, which is equals to 1, -2, and T, number B, find the image of X, which is equals to X1, X2, and T, and number 3, find the range of T. Find the range of T. Okay. So if we have that transformation, looking at this, how many number of rows are here? So the columns are here are what? 2. So the number of entries rows there are 3. So it is from R2 to R3, from R2 to R3. Now let's find the image of U, which is equals to 1 and 2. So it is equals to 1 and 2. So if we have A to be equals to 1, 2, 2, -1, 3, 0, and then we have our U to be equals to 1 and -2. So what will be our image? So what will be our image? So we know that this is a transformation from R2 all the way to R3, from R2 all the way to R3. So here our image, we say that our image from our definition here, for any x element of Rn, T of x is called the image of x. And we said this T of x is equals to what? A of x. This T of x is equals to A of x. So then T of U in our case is equals to what? AU. T of U equals to AU. So then this T of U will now be A, which is 1, 2, 2, -1, 3, and 0, multiplied by what? U, which is 1, and negative what? And -2. And we get our T of U there. So our T of U here will be what? -3, 4, and what? And 3. -3, 4, and 3. So that is our image. So T of U is what? Is the image. T of U is the image of T. Now, number B. So this is A. So B. Find the image when x equals to x1 and x2. So what is the image of x under T? So it's the same thing. So this is a transformation from R2 to R3. And our x is an element of R2. Our x is in R2 because we have how many entries there? There are 2 of them. So our x is in R2. Then T of x equals to what? AX. And this is in our what? R3. AX, which is in R3. So then we have 1, 2, 2, -1, and then 3, 0, and what? X1 and X2. X1 and X2. Then this is equals to what? This is the same as x1 multiplied by 1, 2, 3 plus x2 multiplied by 2, -1, and 0. If you still remember how we multiply the vectors, the vector and the matrix. So you can take this multiplied by x1, take this multiplied by x1, and then you add. So basically, this is the same as x1 plus 2x2. The next one is 2x1 minus x2, and then lastly 3x1. 3x1. So that is what we get. That's what we get. Now, finally, what is the image? Number C, what is the image? So the image, so from our definition here, the image of T equals to T of X, such that X is an element of what? R2 in our case here. That is our image. So if this is our image, then we already know that T of X is the same as what? T of X. So then this is equals to x1 plus 2x2, 2x1 minus x2, and then 3x3, 3x1 there. Such that x1 and x2 are elements of what? R2. Such that x1 and x2 are elements of R2. So then, not even R2. These are constants. These are what we are looking for. They're real numbers. They're real numbers. So then, this is the same as, this is the same as, so it's just the same as this, x1, and then we have 1, 2, and 3, plus x2. We have 2, -1, and 0, such that x1 and x2 are elements of real number. X1 and x2 are elements of real number. If you still remember how we were writing this, how can we still write that? How can we write this? If you get this one, I'll give you some partial credit. So how can we write that? Yeah, again, how can we write that instead of writing the whole of this? How can we write it? If you remember that, 5 will be yours. I'm giving you 1 minute to think.
Is there another way you can write that?
Yep.
Okay.
And we talked about it in class. Go through your notes.
Could you write it as just a vector product with a matrix?
We did it like a few days ago.
Yes.
Not too far. I think we did it on Monday, if I'm not wrong. You can write this on S. No one knows it.
I don't have my notes.
So we can write this one as the span of what?
Oh, this.
Of 1, 2, 3, and what? 2, -1, and 0. So we can write it like this. You have it in your notes, right?
At home, yes.
It's in your notes, so we can write as that. So you can also say, you can say, take U to be this vector, and then V to that vector, and then you just write this, the span of U and what? The span of. So that is the image. So that is the image. Okay. Now theorem 1.2 theorem. If we let A to be equals to A1, A2, and these are actually vectors all the way to AN, be an M by N matrix. The range of the linear transformation T from Rn to Rm defined by T of x equals to A of Ax for x elements of Rn is the span of these vectors A1, A2, all the way to AN. So this is just like this example here. So the range is actually the image. So the range is just the same as the image of T. So if anyone asks you the range of T, then the range of T is just the image of T. Just the image of T. So, and it is like this. So we say that the image of T equals to T of X in our case, whereby X is an element of what? Rn in our case. And this T of X, we say this T of X is the same as Ax, such that X is an element of Rn. That is what we just said. Okay. And we know that this X, we know that this is also the same as Ax, whereby X equals to X1 all the way to Xn. And this is an element of Rn. So that is what we also know. Then we know this A is what? A1, A2, and AN. So when you multiply this A1, A2 up to AN by X1, X2 up to Xn, then what you get here is A1 or X1, A1 plus X2, A2 plus all the way to plus Xn, AN there, such that now X1 all the way to Xn are the ones which you are looking for. And these are elements of real numbers. Those are elements of real numbers. So therefore, then this, like what we just wrote it over here, is the same as the span of A1, A2, all the way to AN. So it is the same as the span. So we just prove this. Let's prove that here. So what program are you doing? Engineering?
Mechanical engineering.
Mechanical engineering. So, which year are you in?
I'm like close to a senior. I just transferred over here from another college. I'm still trying to get my classes all transferred over and stuff. So, but just about a senior. Yes.
I had a roommate who was doing mechanical engineering.
I'm sorry to hear that.
He did. He was doing masters actually in mechanical engineering, and he got a job with Intel. He's paid well.
Yeah, it's okay. It's pretty good. Big company.
He just moved to Oregon.
Okay.
he was telling me if you do a PhD, that is when you would earn a lot of money.
Yeah, go those keeps being pushed back.
Yeah.
I'll take just whatever gets me by, as long as I enjoy my work.
Mhm. Okay, any question up to that? Okay, let's do another example. Okay, I'll post this notes in Moodle. Let's do example number 4. Define the linear transformation. And this transformation is from R3 all the way to R2 by T of X, which is equals to AX for X elements of R3, for X element of R3, where A equals to 1, 1, -2, 2, 3, and 4. Now, is Y equals to 5, 2 in the range of T? If so, then find all the vectors X in R3 that has image Y under T. Now, so we want to show whether this Y is actually in here. So the solution, so the first thing we need to do is we want to determine whether AX is equals to what? Is equals to Y. So we want to determine whether AX equals to Y, because that is actually the transformation. Is equals to that. So we want to show whether that AX is actually, this Y is actually equals to T of X, is actually in the transformation. So what we're going to do here is we want to check whether this is what? Consistent. So we want to show whether that one is consistent. So if it is consistent, then it means that this Y is in the range of T, or that Y is actually the image of T. So then we have this matrix A, then we just write the augmented matrix there, 1, 1, -2, and then 5, 2, 3, 4, and then 2 there. And then we reduce it. Then we reduce it. So we reduce this. So what we get is our new R2 will be R2 minus 2 R1. So what we should get is 1, 1, -2, 5, 0, 1, 8, and -8 there. Now, since we have the pivot position of the last row here is not contradictory, this last row here is not contradictory, then it means that the matrix equation AX equals to Y is consistent. So Y is in the range T, is in the range T. Number two, now we need to solve, so we need to solve AX equals to Y. So we need to solve AX. Since we have found that it is consistent, then now we have the solution. So we are able to get the solution. So we need to get the values of X here. So the easiest way here is to reduce this one to reduced echelon form. So we already have the echelon form, which is this. So we want to make this one to be 0 there. So we reduce that again. So we reduce 1, 1, -2, 5, 0, 1, 8, -8. So we want to make this one to be what? 0. So we reduce this. So to get the new R1, then it is R1 minus R2. And what you get is 1, 0, minus 10, 13, and then 0, 1, 8, and minus 8 there. So that is, so we have our basic variable as x1 and x2, and our free variable as what? X3. Free variable as x3. So our new solution here is x1 minus 10 x3 equals to 0, equals to 13. So, and then x2 plus 8 x3 equals to minus 8. So x1 equals to 13 minus 10 x3, so plus. And then x2 equals to minus 8 x3. So our solution set here is x is equals to x1, x2, x3 equals to x1 is 13 plus 10 x3, x2 is minus 8 x3, and x3 is our free variable. So basically this is equals to 13 minus 8 and 0, and then plus x3, 10 minus 8, 1, for any x3, for any x3. That is our solution. Example number 5 is just the same thing, but I will just give it to you and then you will do it at home. Example number 5. Define the linear transformation T from R3 all the way to R3 by T of X equals to AX for X element of R3, where for A equals to 1, -2, 1, 3, -4, 5, 0, 1, 1. Is Y, which is equals to 1, 9, and 4 in the range of T. Justify your answer. Justify your answer. So you will just do the same way, like what we've just done. And then what you will realize that the last row, yeah. The last row here will be contradictory. So the solution is, so if you go do it, then the third row in the last augmented matrix is a contradictory row. So then AX equals to Y is inconsistent. It must be inconsistent if there is no solution. Okay, let's look at the properties of linear transformation. Let's look at the properties of linear transformation. So the first one is we can put 2.1 and we can use this one as a theorem. If the transformation from Rn all the way to Rm is a linear transformation, then T of 0 vector is equals to 0 vector. So that is the first property. T of 0 vector is equals to 0 vector. The transformation 0 vector. So you can it's easy to prove this, so we can prove this one in a minute. So T of 0 vector is the same as T of 0 plus 0, right? That's the way we do. So T of 0, we said we can distribute this T, which will be T of 0 plus 1, T of 0, right? Or T of 0 can also be T of 0 minus T of 0, which is equals to what? 0. Hey, let's look at an example on this. Example number 6 is the transformation T, which is from R3 all the way to R2, defined by T of x1, x2, x3, which is equals to 2x1 minus x2 plus x3, x1 plus 2x2 minus 5 for x1, x2, and x3 elements of R3, a linear transformation. Is this a linear transformation? So using this property here, then we want to show that whether this one is a linear transformation. So what you need to do is you can let these to be 0 vectors, okay? So is this T of 0, 0, and 0 equals to where there is x1, x2, x3, you put 0. 2 multiplied by 0 minus 0 plus 0, 0 plus 2 multiplied by 0 minus 5. And this is equals to what? 0 and what? 5. Is this equals to 0? It is not equals to what? 0 vector. So that is not a linear transformation. So it's not a linear. See, we say T of 0 should be equals to what? Is this 5 or minus 5? So it is not equals to 0. And this 0 vector is just 0 and what? And 0. 0 vector. Another property 2.2, which is also a theorem. And this is actually it's another way of defining the linear transformation. A transformation T from Rn all the way to Rm is a linear transformation. If and only if T of C1 U1 plus C2 U2, and these are vectors, is equals to C1 T of U1 plus C2 T of U2 for any U1 and U2 elements of Rn and C1, C2 element of U1. So this is another way of defining the linear transformation. Instead of writing the two of them, remember the two of them, T of U without this and this equals to T of U and T of U, and then the other one was T of C U equals to C. So this is the easiest way of defining the linear transformation. Okay. Now theorem 2.3. So you can look at how to prove this. It's in your textbook. If the transformation from Rn to Rm is a linear transformation, then if we have T of C1 U1 plus C2 U2 plus all the way to Cn Un, these are vectors, then this is equals to what? C1 T of U1 plus C2 T of U2 plus all the way plus Cn T of Un. It's just similar. If you have more than two vectors for U1, U2, all the way to Un, elements of Rn, and C1 all the way to Cn, element of real number. So, and then finally, in this section 1.8, let's look at an example. Number 7, example number 7. If we let E1 to be the standard vector, which we did in 1.9, we let E1 to be the standard vector, which is equals to 1, 0, 0. E2 to be another standard vector, which is 0, 1, 0, and E3 to be the final standard vector over 3 by 3, which is 0, 0, 1. Y1 to be equals to 1, negative 1, and Y2 to be equals to 0, 1, and Y3 to be equals to 1, 1. If those are, if we let that one to be that, if the transformation is from R3 all the way to R2, is a linear transformation such that T of EI equals to YI for I equals to 1, 2, and 3. Then find T of 2, 3, and 4. And T of 2, 3, and 4. We have this if T is from T and T, then find T of that solution. So we can actually express this one as a linear combination of the standard. So we can express this as the linear combination of the standard vectors, whereby 2, 3, and 4 is the same as 2 and then 1, 0, 0 plus 3 and 0, 1, 0 plus 4 and 0, 0, 1. It is still the same because if you open this brackets here, it will be this is 2, this is 3 here, and this is 4 here. When you add them, you still get 2, 3, and 4, right? You still get that. Then this is equals to 1, 0, 0 is what? E1, E2. So it is the same as 2E1 plus 3E2 plus 4E3, right? Right. Now, when we now introduce the transformation here, when we now bring the T here, we bring the T here, then it will now be our T, 2, 3, and 4 equals to what? T, 2E1 plus 3E3, 2 plus 4E3, right? Right? And then we can distribute this T inside here, which will be what? 2TE1 plus 3TE2 plus 4TE3. E3. And what is TE1, TE2, and TE3? So TE1, TE2, and so TE1 is the same as Y1, TE2 is the same as Y2, TE3 is the same as Y3. So this is actually equals to 2. TE1 is the same as Y1 plus 3Y2 plus 4Y3. And we have Y1, Y2, and Y3 are here. So it is the same as 2, -1, and 1 and -1 plus 3, 0, 1, and then plus 4, 1, 1. And we open that brackets, what we get finally is 6 and 5. And that is the solution. That's the solution. Okay. That is the end of section 1. So when we meet, then we can go through 1.9, the sections that we already did. So we'll just go through and then we do the final part of 1.9. So the first exam will be on 1st of June. 1st of June. And it will be the same time here, which is from 1. The exam will not be too hard to 2:15 p.m. It will cover chapter 1. Just chapter 1. So it will be 1.1 up to 1.9.
Are we gonna review for that all on Tuesday?
Yep, I'll send you the review before. I'll work on it today and tomorrow.
I'll study guide.
Yep.
Cool. Sounds good.
Yep, so we will meet tomorrow. Okay, so see you guys tomorrow.
You start bringing lunch to class with me.
Yeah, you need to be bringing lunch. I thought you have a wife.
What's
I'll be cooking for you.
Right, well, she's working. I just come straight from work and then go straight back to work. This is my lunch break.
Yeah, you should be cooking before